Okay, this section is called Earth-like planets. It's about Venus and Mars. We just finished talking about the cratered worlds, the Moon and Mercury. These planets are a little bit more Earth-like, and they both sort of have atmospheres and are a little less cratered. So let me start by just talking a little bit about some of the major properties of them here. So as compared to the Earth, if I on most of these, the scale is where Earth is a 1, not all of them, but so if the Earth is a 1, the semi-major axis is, this is the size of their orbit, roughly. The Earth is 1 astronomical unit. Venus is about 72% of that, and Mars is about 1.5 times that. And so Mars is outside Earth's orbit, and Venus is inside Earth's orbit. Their years, if Earth is 1 year, Venus orbits in about 0.6 of that. Venus's orbital period is about 220 days. Mars is about 1.8 that, and so it's I forget 600 and something days, 680 days maybe. If the mass of Earth is 1, Venus's mass is about 0.8, and Mars's mass is about 0.11. In other words, about 11% of the Earth's mass versus 80% for Venus. So Earth's diameter in kilometers, you can see Venus is almost the same size. Mars is about half the diameter. Notice the density. Venus and Earth are about the same. Mars is significantly below. Mars is further out towards the outer solar system where things get less dense for reasons we've talked about a little bit about, but we'll talk about more as we go. Surface gravity, this is kind of a mass type issue. Again, escape velocity, same way. So here's the rotational period. Earth's sidereal period is about 23.9 hours. Venus has a rotational period, in other words, its day is 243 Earth days. In other words, it rotates super slow. It takes longer to rotate once on its axis than it does to go around the sun. And so Venus is kind of exceptional in that regard. Mars's day is about 24.6 hours. Surface area, that's just basically similar to its size. The next significant one is its atmospheric pressure. If Earth's atmospheric is 1, we can use the term bar. That's 1 atmospheric pressure. You can call it just an atmosphere if you want. Venus' pressure is 90 times the Earth's pressure. So Venus' atmospheric pressure is way high, and Mars's atmospheric pressure is less than 1% of the Earth's pressure. So these are two extremes, and the Earth is sort of the Goldilocks. So let me just do a little geometry here. So here's the Earth's orbit. Let's put Venus's orbit here. This will be Venus's orbit. Maybe I'll put Mercury's orbit in here too, somehow. This is Earth's orbit coming around here like this. That's not very good. And then we'll put Mars's orbit out here somewhere. And so we'll call this, this is Mars's orbit. I'm going to put Mars in different places, just like I'm going to do with all these guys. I'm going to put the Earth over here. So here's the Earth. This is Venus's orbit. Here's Venus, and here's Mercury. You'll have to know that one of the M's is Mercury. This is the Mercury M, and this is the Venus M. Maybe I'll make this guy a lowercase m. Just make everybody happy. So one of the things we notice is that if you're looking from wherever the Earth is, Mercury is always within a certain angle of the sun, right? The farthest Mercury will be from the Earth. Doesn't matter where the Earth is. If the Earth is over here, right, then still the widest angle the Mercury can be from the sun is like this. Same thing with Venus. The widest angle you would get would be this way to that way, right? This is the farthest angle you can get away from the sun. There's the sun, right? Anywhere else Venus is in its orbit, it's at a smaller angle to the sun than it is out here. And so for inner planets, For Mercury, it's about 28 degrees. That's the maximum angle Mercury can be away from the sun. And so if you're, if the sun just sets, the farthest, if Mercury's in the sky, it's within 28 degrees of the horizon, always. I forget what it is for Venus. Maybe 45 or something like that, I'll say. So I'll put an exclamation point that one for sure. This is called the angle of maximum elongation, the farthest it gets away from the sun. So if we go back to that picture, right, I'll draw my sun again. Mercury, Venus, Earth. I'm just going to put Mars out here, right? Here's Mars, something like this, right? So here's Earth. If I was standing on the Earth, hopefully you can figure out, so if the Earth is going this way and rotating like that, this would be sunset for me, right? The sun would be on my horizon. I'd be looking to the west. My Earth is turning this way, right? If the sun just sets and Venus is right here, there's my Venus, then just as the sun goes down, I can see Venus above the horizon, right? But only for a short time. By the time it's midnight, Venus will be below the horizon for me, right? Because this is not a scale drawing, and I wouldn't be able to see through the Earth to see that way to see Venus, right? Mars, on the other hand, can be overhead, right? And so Mars can be overhead at midnight, unlike these guys. Here's midnight for me, right? These guys I'm not going to be able to see very easily at midnight because they're close enough to the sun that by the time the sun's gone below the horizon, a few hours later, they're going to be below the horizon as well, and then I'm not going to be able to see them anymore. But Mars and all the outer planets can, at least at some time during the course of a year, be overhead at midnight. This position is called opposition. So when we want to send a probe to Mars, we wait until we're coming up on it, right? Since we go faster, we're going to be catching up to it, and it's going this way, and so we might be here, and we'll send a probe to it. And so all of these probes we send happen just as we're getting ready to go by them. We launch them as we're getting ready to go by, so that as we're approaching opposition, this gives us the maximum, the minimum distance to travel, right? We wouldn't want to launch, when Mars is over here, we wouldn't want to launch a probe from over here. It would take forever to get to it and take a lot of energy and stuff like that. So we just use the shortest trip. And so if you ever watch like a video on a Mars mission, like the recent Perseverance lander, these guys have a 2-week window to launch, and everything has to be good to go in that 2-week window. And if they don't, they've got to wait till this comes all the way around again, right? So did I say everything I want to say? That angle is maximum elongation. By the way, these inner planets are called inferior planets. So we talked about this a little bit before. Mars and Venus are called, Mercury and Venus are called inferior planets because they're inside the Earth's orbit. They're closer to the sun. So that's Mercury and Venus. Mars through Neptune, so Mars, Jupiter, Saturn, Uranus, and Neptune are called superior planets. They're outside. So superior planets can be seen in opposition, right? Because they'll be coming around outside of us. inferior planets can't be. Okay, let me go back to this. So if I come over here and I scroll down a little bit. So if you look at this table on the right is the sidereal period in years. The sidereal period is just how long it takes that planet to go around the sun, and this is in Earth years. So it takes about a quarter of an Earth year for Mercury to go around the sun. That's about 3 months. It takes about 6/10 of an Earth year for Venus to go around. We already talked about. That's 222 days, and so on for these guys. The synodic period is a little different. It's the time it takes to go from the same orientation around the Earth relative to the Earth. The time it takes to go from one to the next. So, for example, the time for Mars to be at opposition and then to go around it being in opposition again is 2.1 years. Notice that's not the same as the synodic period. The synodic period is 1.8 years. And so they're not quite the same. You might notice that these guys are pretty close to a year. Neptune moves so slow that it's only moved a tiny bit by the time we go around one time and it's in opposition again. So let me go back and draw these guys for you one time and show you what I mean. See if I can make this clear. So let's pick Neptune. So here's the sun, right? And here's the Earth. I already showed you a video with the planets moving. I showed the inner planets move a lot faster. So let's say this is Neptune way out here. I know this is not a scale drawing, but that's fine. We'll say this is Neptune, right? Notice if you look at the table that we showed a second ago, let me just pull it back up here real fast. You can see that Neptune's sidereal period there on the right is 165 years. It takes Neptune 165 years to go around the sun one time. That's what that means, right? And so let me go back. And so that means while the Earth goes around one time, Neptune has moved about that far. One Earth year. And so to go from one opposition to the next opposition takes slightly more than a year. And that's why when you look at this table, you see the synodic period is 1.006 years because Neptune has barely moved. It's trickier with Mars, right? And with Mars, where it takes 1.88 years to get to do one period, one sidereal period, it takes the Earth quite a bit of time to catch up. So if let me just switch screens here. So if this is Earth and Mars at opposition, then when the Earth is back around here 1 year later, Mars is up to here, and so it's done a little more than half a lap because a full lap is 1.88 years, and so 1 year is a little more than half. So Mars is over here somewhere, and then by the time it gets to 2, Mars has gone still a little further, and so the next opposition, the Earth has done 2 laps and a little bit to get to here. So this would be like 2.1 years. And then the Earth comes all the way back around. It's going all the way back around and gets to here. And that's where the Earth is at their next opposition, and so on. And then the one after that, they'll meet here, and the one after that, they'll meet here, and so on. Each time it takes the synodic period of Mars is about 2.135 years. So